Hello and welcome back to Precalculus, section 6.6 on vectors, basics of vectors. So, in mathematics, we describe variables as scalars and or vectors. Now, there's more to that, but these are the two that we use most often. And the vector, or the scalar and the vector is not the same thing, obviously. So now we want to learn what is what. Now, the scalar quantity would be something that only has a numerical value, like let's say time. You know, time flows forward. If you wait a little bit, it would be 15 seconds or 15 minutes from the time you started waiting. If you look at the time, it has its direction going forward. You don't really have the time going backwards. So the direction doesn't matter. It is just a number. So when you say 5 hours, it's just number 5. And it is just the size of the number, right? So it's 5 hours or it's 10 hours and so on. But if you take a look at, let's say, speed and velocity, right? Speed is how fast you are going, but velocity is a speed plus another piece of information, and that is which way you go. Because if you think about it, right? If you are joining, let's say this is where your house is, in your driveway, and now the speed limit is 25, and you're going to drive 25, but you're going to drive 25 this way, or you're going to drive 25 that way. Right? It depends where you're going. I understand that. But the thing is that now I need two pieces of information to describe this phenomenon. I need a piece of information that is telling me that you are going left or right, and that one is going to be called direction. And then the other piece of information is the fact that you are doing 25 miles per hour, which would be your speed. So now speed and direction put together is going to be called velocity. And that would be something that we, in mathematics and physics and other STEM courses, right, we would, something like that we would call a vector. Now, anytime when direction and the number, which we are going to call magnitude, is important, when they are both important, we are going to call that a vector. And in other cases, where you just need a number, as example, I gave you time, right? In that case, there will be a scalar. Now, scalar has only a numerical value. Your height is going to be a scalar because it's just a number. You are 5 feet tall, or 5.5, or 6 feet tall, right? That's it. There is no other quality to that other than just a number, just like a time. Where force is how strongly you push, but also in which direction you push. Because if you are supposed to push this fridge, right, to its location, and you are standing right here, and you push this way, well, with all of your strength, teeth clenched and everything, it's like you're like ready to push this fridge, but just push it in the wrong direction, and yeah, nothing happened, right? Fridge did not move. You have to push in a correct direction. So force is going to be a vector because it's not just how strongly you push, but also in which direction you push. Same like, as I said, velocity. It's the direction in which you are driving along with the speed at which you are going. And obviously, everyone would quickly agree that it's important to have the correct direction when you are driving. So vector is a mathematical construct. They don't exist. You don't see a vector walking down the street. We use it to describe things. So vector is a mathematical construct which has direction and magnitude. It will be represented in the xy coordinate system as the arrow. You can call it a vector v, and you have to put this arrow on top. Now this vector v will have two coordinates, and now instead of parentheses you are using these spiky brackets. Now vector is going to connect 2 points. Initial point P and the terminal point Q. Now, point P is going to have, let's say, A and B. Let's go with x1 and x2. x1, y1 coordinates, and point Q is going to have, let's say, x2, y2 coordinates in the coordinate system. So the vector PQ is the terminal point minus the initial point. So x2 minus x1, comma, y2 minus y1. Force, velocity, acceleration. What else we can do? Wind, right? Because it has a direction, and fluid flow, flow of traffic. A lot of different vectors. And the scalars, we said time and the height, and so on. Okay. So now what? Well, we can say that when I have a vector in the coordinate system, we can drop this line like this, and you see an x over here, you see a y over here. So we can find the magnitude of the vector denoted with the absolute values as simply your Pythagorean theorem. It's a triangle. It's a right triangle, nothing new, nothing special. You all understand that. So once you have this magnitude, you can look at the direction, and that's going to be the angle that the vector has towards the positive axis. And that one is determined by so direction is going to be theta, and it's going to be inverse tangent of y over x, because your direction is the angle theta. So your tangent is y over tangent theta is equal to y over x. Therefore, theta is inverse tangent of y over x. And these are very important as well, because if you want to know how strongly something was pushed, let's say, well, you have to know the magnitude of the vector. And if you want to know which direction things were pushed in, right, then you need to know angle theta, because the direction in which the push occurred is angle theta. And now you can combine this with your bearings and all of that stuff to come up with technically everything we need. Okay, so what are we going to do next? Let's take a look at vectors. That vectors can be, well, let's do the component vectors first, and then we're going to add and subtract and do all of that fun stuff. So when you are, and it's good to have the square grid, obviously, to understand this next piece. If this is the standard XY grid, there's going to be a vector that stretches up to 1 and another little vector here that stretches up to 1. Those little guys are called the I and J unit vectors. Now you might wonder, what is this little hat on top? And it's literally red hat. It is the notation for the unit. So when you see the word unit, whatever vector you have, it will have a hat on top. Now I need to explain all of that. Obviously, it's just a notation for now. What is the meaning of the unit? Means that the vector magnitude is 1. So the word unit here, or let's just go with the unit vector, means magnitude is 1. And that is a very important concept, because a lot of your formulas in the future will use unit vectors. Because unit vectors carry the direction and they don't change your... so unit vectors carry the direction, but they do not change the magnitude or strength of the force or something like that. Now, vector I, unit vector I hat, is defined as 1, 0, and the j hat is 0, 1. Now, if you look at the picture, you see that the terminal, the initial point is 0, 0, and the terminal point for I is what? Terminal point for y is 1, right? In every case. So now let's take a look at why these little guys are important. If I have a vector which is, let's say, right here, and I want to know what that vector is, I'm going to line up all of these little guys and I will have, so let's say this is a vector V. Vector V will have 6 I vectors and it will have 3 J vectors. This is a vector 6, 3. So now you have two different components in which you can, right, which you can use to show your two different ways, representations to show your vector. And let's see. Do we need? We can deal with that later. Okay, so let's take a look at, let's say, a negative vector. I mean, negative, one of the components or both components, doesn't matter. It follows what you know from before. So let's say this is your vector here. Let's call this vector u. You have 1, 2, 3, but it's on the negative side. So vector u has a negative 3i and it has positive 2j. And that vector can also be represented this way. There are actually more representations of vectors than this, but for right now, these are the only two that we are covering. There are more representations for vectors, which is, in my never humble opinion, awesome, right? I know it could be, confusing for people, but there are polar forms and a whole bunch of other stuff that we are going to see eventually. Okay, so what's next? Unit vector. Oh, that's going to be division. I have to, hold on, before unit vector. Let's add and subtract vectors. And we will do this in two different ways. We will do it using their written form, right, with coordinates, and then we'll do it graphically as well. So I'm going to take vector u, which is, let's say, 3 and 6, and the vector v, which is, say, 1 and 3. And I want to add these two vectors. Okay, so u plus v is going to be 3, 6 plus 1, 3, and you just add their components to 4, 9. You can also do this using the ij notation we just learned, where you can say 3i hat plus 6j hat plus, so that's my first vector, right, plus my second vector, which is just I hat plus 3j hat, and that's going to be 4i hat plus 9j hat, because 6j plus 3j is 9j. We don't need these parentheses in the front. I just wanted to make sure that you see the first and the second vector, and then this is the main plus in between the two. And subtraction is going to work the same way. But let's add them graphically. This is the interesting part. We'll need a little bit more space on top because we have to go all the way up to 9. So let's make, and we don't have any negatives, so I hope this is going to be good enough. And we're going to draw our two vectors. The vector 3, 6. 1, 2, 3. Right? That's my I vectors are going 3 to the right. And then J vectors 6 up. 1, 2, 3, 4, 5, 6. And we connect that right there. And this would be our vector U. Now, vector V goes 1 unit. Actually, I gotta move this U. Let's move it here. I have to go 1 unit and then 3 up. There we go. So this would be vector V. To add vectors, you simply move vector V to the tip of the vector U, which is why this is called head to tail method, because the this vector now, the vector V, is going to move and add right here. And as you can see, it is still, I'm going to erase this, it is still 1I and 3Js. So you can think of the tip of vector U over here, you can think of that as the new coordinate system in which you are going to put new vector, right? And you want to put new vector in that coordinate system. So all I did is I went at the end of U and added V on top of it, and you can see that it's still 1, 3, right? So this is my vector V, and now there is this resultant vector, if I can draw, the vector R. Resultant vector R is vector U plus vector V. Generally, we use lowercase letters for vectors because the uppercase letters will be reserved for matrices later on. It's not, I mean, it's not going to kill you now, but I guess if you start with the correct notation, life will be better later. So don't do what I do. So what is the deal over here? If you take a look at this point, it's going to be 4, 9. Is it? Well, here's where 4 is. And if you go all the way up, you're going to hit that point. Awesome. And here is where 9 is. And if you go all the way out, you hit the point. So, yeah, 4, 9. It's a 4, 9. So that's the graphical way to add vectors. And those of you going to mechanical civil engineering, you will be actually doing this by hand a lot, especially when you're trying to work the bridges and trusses and a whole bunch of other stuff that is coming up. So we have seen what seem to be 3 different methods, but they all boil to the same thing, technically adding components to the mix. Now, before we do subtraction, we have to talk about scalar multiplication. Because subtraction actually doesn't exist. I know it's weird, but let's sit on it for a second. Scalar multiplication will change the magnitude of the vector, but not its direction. Changes the magnitude. Okay, so it changes the magnitude. If I take a vector u and multiply it with some number in front, then that number will multiply each component of the vector. You would technically say, oh, it distributes. Yes, it distributes. That's what's happening. So we are going to now take a look at the example where, let's say, we want to take, what do we want to take? Some value, let's say, well, just make it up. Let's say u is equal to -6 and 13, and c equals to, let's say, 4. So how much is cu equal to? And that would be 4 times -6, 13, which is -24, 40, 52. 52. You can also have, actually, I gotta move this a little bit down. I didn't box anything over here, it's terrible. There we go. So scalar multiplication. No, I don't want that to be red down there. Go away. There we go. Go away. All right, so another example. Let's say v is equal to, I don't know, 18 and -4, and your scalar is 1/3. This is going to make the vector shorter. So CV is going to be 1/3 of the vector. 18 divided by 3 is 6, and then -4/3. It's okay to have 4/3 as a coordinate component. So why is this important? It's important because your subtraction is defined, your u minus v is defined as u plus -1 times v. So the opposite of the vector, right? That's what we have. Opposite of the vector. What it does is just turns the vector around, turns the vector in a different direction. It's still the same vector, but it has different direction to it. So let's see what we can get for that. So if I want to subtract, let's say u is 6 and -4, and let's say v is 1 and, can't even think of numbers, 9, doesn't matter. So these are the two vectors. How much is u minus v? Well, when you're doing calculations, sure, just do the subtraction. The reason why we had to define that thing is because of the addition of vectors. That's our issue. Graphical solution. But over here, I can just say 6, -4 minus 1, 9, and then just say 6 minus 1 is 5, and -4 minus 9 is -13, and I am done. Component form is going to do exactly the same. You are going to have your 6i minus 4j, and that is going to subtract I, forgot the hats, oops, I plus 9j. So 6i minus 1i is 5i. And then minus 4 minus 9 is minus 13j. Obviously same answer is up there. But now, when we do the graphical approach to this subtraction, it will hopefully become clear. Now, let me see. It's gonna be terrible to draw. I need 22 squares. All right, let's see if we can somehow squeeze all of this in. Actually, you know what? If I put this to be 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, and then definitely don't have enough for 13 below, but I can always scroll. So let's put in our basic vectors. It is 6 and minus 4. So 1, 2, 3, 4, 5, 6, negative 4. 1, 2, 3, negative 4. So now I have my first vector. That's vector u. And then vector v is 1 unit this way and 9 units on top. There we go. So that's going to be this vector here. There we go. Now, u minus v is equal to u plus negative 1 times v. So, my vector u is what we have, which is still 6, negative 4, plus, and my vector v gets multiplied by negative 1, so vector v becomes negative 1 and negative 9. But that's not what I have on the picture. The picture shows 1 and 9. So I have to draw the negative 1. So here is the negative 1. 1, 2, 3, 4, 5, 6, 7, 8, negative 9. And then I need negative 1, so it's right here. So this is my negative v technically. And now when I move, I need these dots. When I move this vector here, you will see that they add to what we need. Is this by any chance 9? 1, 2, 3, 4, 5, 6, 7, 8. Holy nightmare. I just did a random line and I got it. Okay, so I am now adding u plus negative v. And the total, which is the resultant, let's see if I can do a better job. It's a little bit rocking on my cooling pad. Resultant vector here, r, is addition of the vector u as is and the opposite vector, which is vector v. So now we are set with this, and we have our value, right? We have our sum of these two vectors. All right, well, cool. What's next? All right, now that we have all of our definitions and things, we can define the unit vector, because anytime you need the unit vector, you will use the formula. So u hat, any vector, is going to be vector u, vanilla vector u, divided by its magnitude. So that's that. And let's say find unit vector for, say, vector u is equal to 6 and -4, whatever. If you look at the formula up there, you need the magnitude. And the magnitude is just basic Pythagorean theorem. We had that at the beginning of the lecture. So that's 36 plus 16, which is the square root of 52. Now that is 2 root 13 if you care about simplifying values, because 52 is 4 times 13. It's like a deck of cards, right? And now I can calculate the unit vector. It is vector u divided by 2 root 13, which is 6 over 2 root 13, comma, -4 over 2 root 13. And now we simplify, rationalize, and we're done. That's 3 over root 13 and -2 over root 13. Now we just need to multiply by root 13 because we need to get rid of those in the denominator. So the unit vector is 3 root 13 over 13 and -2 root 13 over 13. Magnitude of this vector is 1. And the direction is the same as u. So we calculated the magnitude of the original vector. And we see that the magnitude of the original vector is 2 root 13. So original vector is clearly not a unit vector because it has magnitude of 2 root 13. However, the unit vector, right, we divided the vector with its magnitude. So the unit vector that we have on the bottom does have the magnitude of 13. Sorry, of 1, because we scaled it down. Now you can check, obviously, by finding the magnitude of that vector, which is actually pretty simple. These squares are going to kill the roots, and it's just going to quickly work out. If you take a look at these and square them, you're going to have 9 times 13 over 13 squared plus 4 times 13 over 13 squared, and the square root of that. Because 3 squared is 9, then square kills the root, so 9 times 13. And, you know, again, quick computing, instead of reaching for the calculator to go through all of this nonsense, hold on, just cancel one of the 13s. Cancel this 13 and 1 on the bottom, cancel this 13 and 1 on the bottom, and what are you left with? You're left with the square root of 9 over 13 plus 4 over 13, and that's already common denominator, which is square root of 13 over 13, which is square root of 1, which is 1. Yay. So we do have magnitude of 1. It's a unit vector. Awesome. And then we have, I also said that the direction is the same as the original vector. Well, that's also easy to check. It's just the inverse tangent. And we don't even have to compute it. We just need to compare it to the original problem, which is negative y over, y over x, which in our case is negative 2 root 13 over 13 divided by 3 root 13 over 13. Well, the root 13 cancels root 13, and 13 cancels 13. So it is tangent inverse of negative 2/3, which is negative tangent inverse of 2/3. And I'm not going to actually bother computing this in a calculator, because all I need to do is to compare it to the original vector. And the original vector had negative 4 and 6. Negative 4 and 6, which is negative tangent inverse of 4 over 6, which cancel to 2/3. And you see they're the same. So unit vector has the same direction. Unit vector has the same direction as the original vector, but it has the magnitude of 1, where original vector does not have magnitude of 1 because it's not a unit vector. We have some properties of vectors, and we can take a look a little bit more at some of the problems. So this is the last part of the theory. Let's go blue. Properties of vectors. And these are mathematical formulas which are true about vectors. So, oh, I didn't give you the zero vector, huh? Zero vector is 0 with the arrow on top, and it's just 0, 0, or 0i plus 0j. You can add more dimensions. All right, so what are the properties? Property number 1, addition is commutative. I hope no one is shocked by that. 2, associative property works. So u plus v plus another vector w, we can add v and w first, and then add u to that. 3, if you add a zero vector, let's not add, if you add a zero vector, or you add your vector to a zero vector, you will always get your original vector back. Again, nothing shocking. And then if you add the vector to its opposite, they add to 0. Well, that should be common sense too, right? Because 3 plus negative 3 is 0. So it works for vectors too. Why wouldn't it? Now, scalar multiplication, if you have multiple constants, says that you can multiply those first and then multiply them into the vector, or you can multiply one into the vector, leave the other one. So you can have any combination. Distributive property also works, and we actually have a couple of them because we can have multiple vectors or multiple constants. And that's just cu plus cv. So that's what you guys are used to. as a distribution, right? 3x minus 6 is 3x minus 18. Distribute in each. Distribute in each. Same thing. 7 is, this is what I said, multiple constants, and you can also distribute the vector. Cu plus du. I hope you're sitting down. If you multiply vector u by u, you get u. If you multiply vector u by 1, you get u back. And if you multiply it by 0, you get a 0 vector. Yeah, 0 times 10 is 0. Awesome. And finally, the last one is that the magnitude of c times vector v is absolute value of c times the magnitude of v. So this is magnitude. And you will see sometimes people use 1, sometimes they use 2 of these absolute value type of brackets. It's just a notation. We know what it means, so we just use it. Okay, so now what else can we do here? We can do some problems. Let's go to homework and see some of the problems that they have. All right, try to navigate through this. This is problem 37. They want you to compute magnitude of this subtraction, and they give you that the vector u is 2i minus 5j and w is minus I minus 6j. So try this problem on your own for a minute or so. Should go quick. Should go quick, I hope. Okay, let's take a look at the problem together. So we are looking for the magnitude of these two vectors. Now, if you don't like ij notation, that's okay. You can write it as 2, -5. I mean, it's less writing maybe. And then -1, -9. No, -6, not -9. -6. And now we subtract. So 2 minus -1 is 2 plus 1. That's a 3. And then 5 minus -6 is -5 plus 6, which is +1. And the magnitude for this is 3 squared plus 1 squared, which is square root of 10. So the answer is square root of 10. And no, you don't have to calculate square root of 10 and provide decimals, because square root of 10 is the exact value. Anything else is approximation. Let's see what else we can find. Oh, and as I said, this will be used in physics, because our book, right, has a crate on an incline. And if you think about this, you are going to have a couple of these forces that are playing the role in this for this crate. This is the weight. This will be the normal force and the resultant in between. Well, the normal force goes like this. That's the opposite of normal force, so minus n. But the normal force is always perpendicular to the surface, and the normal force is the one that is responsible for the friction, for instance. It's the part of the friction formula if you study physics. So in a problem like this, right, when you know this angle theta, then that's the same angle theta there. And look, you have a triangle. And you know one angle, you know the weight, you know the normal force, because both of those are related to the mass of the object. And if you know those two, you can find the resultant on the bottom. It's really cool. And a lot of your physics problems will land in that realm. So that will be it for vectors. I will open the homework, try a whole bunch of exercises, addition, subtraction, scalar multiplication, and to obtain vector given 2 points. I know I did this and I gave you the formula, but just in case, one more time, if you need to go from point A to point B, you can have a vector stretch in between those. Then vector A, point A is -2, -2. And B is 1, 2, 3, 4, 5, 5, 1. To find the vector AB, you will take B minus A, comma, by value minus A value. So vector AB is 7, 3. And if you count, you actually see that it's 7, 3. 1, 2, 3, 4, 5, 6, 7, 3 up. 1, 2, 3. Good. Works. I mean, so of course it's going to work. It's math, but yeah. So if you are given 2 points in space, you can stretch the vector in between them, and that vector will give the direction. And the stretch, the distance between, is the magnitude. So both of the concepts you guys learned have something that have some importance in that. Yeah. So that's the introductory talk on vectors, and you are going to get so much more in physics and other engineering courses. This is just knowing what these vectors are as I said, mathematical construct. It's not something that you see walking down the street. And ask questions once you try the homework. Bye.